Well, hello again. Are there now any questions to the previous two paper sheets and wave impedance in electromagnetics? Well, if not, I will like to draw your attention to another phenomena which is quite important. So, now let us consider our quite well-known electromagnetic field that is propagating from this side there. So this is the z-axis. But unlike in our previous case, we will put a conducting plane on which the wave would come perpendicularly. So we would have a conducting plane, a full conductor, perfect conductor. And the plane wave would arrive and land onto it exactly perpendicularly. So we can watch it in two specific views. The first view would be that one in which the electric field of the incoming wave would be oriented in this direction. So we would have a wave with the electric field pointing in this direction. Now that would mean, if the wave propagates that way, that would mean that the magnetic field must point out of the screen. So this is the H. So that the resulting electromagnetic wave carries power in this direction of propagation. So this is fully true as far as that wave reaches our conductor. And we have first stated that this is a perfect conductor, so that a perfect conductor is first defined by the fact that it has so movable charges inside it that it is impossible to create a tangential electric field strength component within it. It's impossible to create any electric field component within it, but for us it's important that it also applies to the tangential field. So at any case, there could not be any value of an electric field strength pointing in this direction. But the wave which arrives has just this direction of electric field. So then something must happen. And that something which happens is that the wave should reflect. By the way, you have a very good experience with that. You use mirrors. And a mirror is, most of the mirrors we use at least, is a thin layer of silver, which is very good conductor. And this layer is mostly stick to a piece of glass, which protects it from oxidation. But anyway, that what reflects is the silver conductor, the best conductor we have available, silver. And it does reflect light, which is an electromagnetic wave. It does reflect it so good that we have a perfect picture. Back. So what has to happen? The only solution to that is that the wave would reflect antiphase, so that there will be an incoming wave with electric field pointing upstairs, and the reflected wave would have the field of the same magnitude pointing downstairs, so that the result just at the surface would be zero. So okay, we could solve that problem if there was, so we have an incoming wave and we have to create a reflected wave that would have the same magnitude but would be 180 degrees phase shifted, or would be in opposite direction. The reflection would be -1 for this case. Well, what about the magnetic field, by the way? Well, let's make another picture at another angle of view. We will turn this so that we will have the magnetic field pointing just upstairs. So now we have another point of view, and we have the magnetic field H incoming just pointing upstairs. We have turned it. And now the magnetic field comes to the conductor. But we know that no electromagnetic wave could exist inside a conductor. Why? Well, because there is no electric field strength. It's impossible to get the field strength into an ideal conductor. So then, if there is no electric field, there could not be any magnetic field of the propagating wave. So somehow it must happen that the wave does not enter into the conductor. Well, how that happens? Well, if you have a magnetic field just at this side of the boundary, how it could happen that there would be no magnetic field on the other side of the boundary? Well, we have to recall boundary conditions at an interface between two magnetics, for example. And what is important is that if there was a sheet of current flowing on the interface, it could happen that it would completely diminish the magnetic field. So how it would work? So let us draw. If I have a small current here, let's say one wire, and the current would flow inside the screen, then the magnetic field of this current would be this one. It would have this orientation. So it would add to the magnetic field in this part of the world, and it would be subtracted from the magnetic field in this part of the world. Now, if we have a number of those conductors, so that they form a plain sheet of current flowing inside the screen, we would find out that if this current, if this plain current density would be 2 times the value of the magnetic field's intensity of the incoming wave. Why 2 times? Because 1 ampere per meter makes half an ampere in this direction and half an ampere per meter in this direction. Each meter of the current has to serve to 1 meter of flux line upstairs and 1 meter of flux line downstairs, or left or right. So we need current density 2 times the incoming magnetic field intensity, which then would result in 0 magnetic flux here. But in fact, it would create the same H with the same direction of a reflected wave. So it seems that the wave that reflects back, H reflected, is of the same magnitude and of the same direction as the incoming wave. Now, is this sound? Well, let us again check it using pointing vector. So we had an incoming wave with the electric field strength pointing upstairs and magnetic field intensity pointing out of the screen, which resulted in a propagation in that direction. It has been the incoming wave. It must have been propagating in the direction of propagation. Now, we told that there is a reflected wave, which has the opposite phase of the electric field strength. Now, I'm telling that the direction of the magnetic field of the reflected wave is the same like the incoming one. But that makes sense. In this case, we would have a propagation back. If we change the direction of both vectors, we would still have the wave propagating into the conductor, but that's impossible. So it follows up that The electric field reflects antiphase, the magnetic field reflects in phase. And this whole thing has been possible only in a case of a perfect conductor. So let's tell the story from the point of view of the conductor. So the conductor rested in space, and all charges on the conductor have been placed equidistant because there was no force moving them, and they repel each other, those electrons, for example, in a conductor. So they have been placed there. But suddenly, there came an electromagnetic wave with electric field strength forcing those electrons at the surface to move. And they started to move. And as they moved, there was a current, because a current is a movement of charges. So the current created a magnetic field, and as the charges moved freely, they moved in such a quantity and speed that they completely zeroed the electric field inside the conductor, which resulted in an electromagnetic wave reflecting back, which had the same sign for magnetic field intensity, but the opposite sign for the electric field strength. So this is the story which we have been telling first from the standpoint of an electric field of an incoming wave, second from a magnetic field of the incoming wave, and third for the conductor which caused the reflection. Well, this is all very fine, but except for superconductors, which so far are known only for low temperatures, the rest of conductors are not perfect. Well, in fact, those conductors are very conductive, like for example silver, but still their conductivity is limited. And therefore, once you have really a current flowing on the surface of the conductor, there is very tiny but non-zero component of the electric field strength which is tangential to the surface. I can tell this story from another point of view. If you have a perfect conductor, you can press some current through a negligibly thin surface layer with no electric field strength. It just means that all the charges can move freely and without creating any heat. But once there is a limited and very big conductivity, you cannot have infinite current density, because with an infinite current density and finite conductivity you would have an infinite power dissipation. And so what happens is, in a real case of a conductor, well, what happens is that at the surface you have some layer of current, which, let's take a magnifying glass. So we have again the boundary with incoming wave, and here we have a thin layer of current. The current flows in this direction and it damps the incoming wave because it has a magnetic field of this constitution up here, down there. So the magnetic field of the incoming wave is damped, but it makes it through the first layer. Well, and then there is a second layer of current, which damps the field once more. And then there is the third layer of current, and then there is the fourth layer of current. And after passing through a number of layers, the wave is significantly damped. On the other hand, this means that first the electric field would not reflect perfectly because there is a small tangential component of electric strength on the conductor, and that the magnetic field would not reflect perfectly because some part of the field reflects on the surface, some part reflects after the first layer, some part after the second layer, and they all get out of the conductor and compose the reflected wave. But as the wave should have get it in and back, there is some time delay and therefore some time shift of the reflected wave. We will discuss this later when we will discuss a reflection of a wave on a boundary of two media. But this important point is for very good conductors. The engineers quite liked the concept of perfect reflection. You have no field in the conductor, you have all the field outside. The wave reflects anti-phase for electric and in-phase for magnetic field. That's a very simple concept. But we should test it. Our test should tell us whether the layer or the layers are very thick, in which this would be a useless concept. I mean, if you have a boundary, you stay 2 meters from the boundary and the whole effect takes 5 meters for 1% decrease. You cannot tell that it reflected on the boundary. It reflects somewhere very deeply in the material. But if it would be 1 micrometer and you observe that from 10 meters, you could easily tell that the reflection was perfectly at the surface. So how to find out how deep the reflection happens? Well, and that is attainable in two ways. So first, we could, of course, get the current density within the conductor and integrate it from the surface to infinity. I will leave that for you as a homework and use that result at the beginning of next lecture. You can also have a value that tells you something. You know, for example, for radiation of X-rays, it's quite useful to formulate something which is called the half depth of penetration, which tells you that, let's say, bricks would damp this radiation to 1/2 if you have something like 60 centimeters of a wall. But not very good. For electromagnetic waves, there is used something which is called skin depth. The skin depth is a distance at which the electromagnetic wave damps just E times, where E is the base of natural logarithms, the Euler's number. So what about this damping? We have the equation that tells us, for example, for E, that it's some E0 E minus j k z, and we remember that this could be decomposed into the real and imaginary part of the propagation constant, which would result in an expression like this: E0 E minus j beta z. This term changes the phase of the signal, but it has absolutely no effect on the magnitude. So this is not important to us, but now there would be E minus alpha z, which is the imaginary part of the propagation constant alpha, and this handles the magnitude of the wave. So we would easily find out that the depth in which this term decreases by 1 could be calculated like the depth of penetration, delta, is equivalent to 1 over alpha and this, for good conductors for which this has good sense, can be found out like a square root of a fraction which in numerator has omega, the angular frequency, mu, permeability, sigma, which is the conductivity, specific conductivity of the material, divided by 2. And this is the depth of penetration, a very important concept, because it enables us to pretend that the current does not flow through the whole piece of the metal we have available, but it only flows in a thin skin, therefore skin effect, in a thin skin which is placed on the surface of the material. Now this skin depth clearly depends on frequency. I will let you one more minute to think about that. Well, nobody tells anything. You could have won a bottle of good wine after the coronavirus, but I have put there an equation for alpha, but then it should be so the skin depth should decrease with frequency, or a square root of frequency should decrease with conductivity, or a square root of conductivity, and the same for permeability. Now this is a very important point that makes us some kind of problems. For example, if you have to design a transmission line for currents for public transport of energy, 50 Hertz, let's say, in Europe, then for low currents there is a rule of thumb. And the rule of thumb says you can get 4 amperes per square millimeter into a wire which is not cooled well. For example, there is a number of wires, number of turns in a coil. Then you can go somewhere up to 4 amperes per square millimeter. If you are designing an open air transmission line, you can get to 10 amperes per square millimeter. Well, okay, this is very nice. And it works for small currents. Why? Well, because if you have a thick conductor, something like a thumb, you have to consider that the current does not distribute through the surface in a good manner. I mean, with DC, you would have the same current density through the whole conductor. But even at 50 Hertz, there is something like 1 millimeter through which most of the current would flow, and you would not be able to get it inside a conductor. But then the current density would be very high at this skin depth, and as the losses are a quadratic function of current density, there would be a lot of loss and the conductor would be destroyed. And at the same time, you would have a lot of losses. So we have a problem which is a problem with skin depth, at least in conductors. The problem is specifically seen at high frequencies. For example, if you have ever designed and built your own radio receiver, it's quite common that you have the RF part somewhere from the antenna to the first amplifying stage, and you have to have there, for example, a ferrite antenna, which is a stick of ferrite with several loops on it. And now it's quite important to have low losses, otherwise you increase your noise figure. So what is available there? If we calculate this number, the skin depth, just to have some idea, at frequencies of 10 gigahertz for copper or silver, the skin depth is something like 1 micrometer. 1 micrometer. So you have a conductor, but the important part which carries the current is 1 micrometer thick. If you have 100 times less frequency, then you have 10 micrometers. So even at radio frequencies of medium waves of AM reception, you have quite a small thickness through which the current really flows, not through the whole conductor, but only through the skin. And the solution for that is that you take a number of very thin wires and you just twist them, so that the surface of the conductors in this conductor is much bigger than would be a surface of a single conductor. The same problem comes for high power devices at 50 Hertz. By high power, I mean generators in the power plant, for example. There you have kiloamperes, and in order to get them through a winding, again there is something like a number of twisted wires for, and now this is very costly. You can easily twist wires that are 1/10 of a millimeter in diameter. You cannot easily twist wires that are 2 centimeters in diameter. So the first thing that is done is that you put several wires in parallel. Just in fact, if you have a big motor, it has a magnetic circuit, then there are some holes through which those windings or loop should be done in this direction, so it's rotating this way. And now the manufacturing process is that you have a number of needles that you put in, and then you connect them at both ends of the magnetic circuit, so that you have much more surface in this. Well, I am drawing circular conductors, but to have a maximum use of the space, this is done using rectangular conductors to save the free space which happens between circular ones. Okay, this is the first solution, but then as the position of those conductors differs against the center of the system, they would have different induced voltages. I mean, if this rotates, a conductor on the outer side would move faster than a conductor here, which would result in a current flowing in between those two conductors, just in the same hole. This should have been one conductor, from the aim of the designer, but it is constructed from a set of parallel conductors which do not have the same location against magnetic field, and therefore you could get easily 1 kiloampere of current just running inside it and heating that. To prevent that, a more sophisticated way is used, which is called permutated conductors, and more or less you have a rectangular conductor and a specific prescription. So inside this you have something like this, a piece of rectangular conductor that, for example, is done that you have another rectangular conductor which goes this way, then you have another rectangular conductor which goes this way. So you have something which needs a very good smith who makes conductors that could be put together, and that's quite a puzzle, so that each of them has the same induced voltage. So the conductor changes its position closer to the center and farther from the center of the machine, and at the length of the stick it has the same induced voltage as all other conductors that surround it. After you put it in, you put there some insulating media which should be resistant to heat, and finally you have a big rotating machine which can bear high currents in its windings and takes into account skin effect in its design. Your questions? Yes?
How was this special cable called with twist in it?
Sorry, I could not hear you properly. Could you
Yes, sorry. How was this cable called with the twist in it that you have drawn on the right side?
Well, this is permuted. Permuted,
Okay.
yeah. It's like permutation in mathematics. Permuted conductor.
Okay, thank you.
Well, so we have now covered another chapter. We have learned that there is something which is called skin effect, and that it can affect the design of electric machines and radio frequency circuits a lot. I would make a last point which will possibly surprise you, but it makes sense to polish the surface. Why? Well, just imagine that at frequencies of microwaves and even terahertz, you have the skin depth of 1 micrometer. So if you have a surface of a conductor and it's done this way, then the current does not flow directly along the surface. Not, it has to copy the surface of the conductor, which more or less gets it 1/2 more long path and increases the resistance by 1/2 and increases the losses by 1/2, which in microwave and radio frequency applications mostly means that you lose your noise number and your signal is damped inside the noise and you can't recognize it. So it makes sense to fine polish the surface of sensitive devices or the conductors. And not only fine polish, then you have the problem with the atmosphere, which is quite polluted in many parts of civilized countries. You have a lot of radicals that would destroy it, especially the acid radicals like the radicals of sulfur. So the acids would destroy the surface, and once you have the surface which is not purely silver, the acid components with silver form something which is only semiconductive, and you have very high losses. So it makes sense not only to polish the surface, but also to protect it by a layer which does not let the oxygen and sulfuric acids and other components of the atmosphere to get in. So that's an important point to learn. Now, if I may, I would ask you for questions. And if there are no questions, I would proceed to another important theorem, another important law of nature, which governs electromagnetic field. Okay, I'll do that. Now let us consider a volume which has no sources of electromagnetic waves inside. So we have a volume with no sources of electromagnetic wave. That does not necessarily mean that there is no electromagnetic wave. It could come from outside. So we have such a volume. And you would probably guess that although this is electromagnetic field, it still is common physics, which means that we have to obey energy conservation principles. So let us consider